Alright, we're going to talk about the electromagnetic spectrum. This is the last part of the electron configuration unit. Whenever you see light or any different colors, you're actually just seeing electrons that are moving different energy levels in the atoms. And when they do so, they produce light of different colors. The different energy levels that they drop, if they drop 1 versus 6 energy levels of a drop, the different amounts of energy levels they drop, the more energy they give off if they drop more energy levels. And that creates different colored light. So that's when we have our visible spectrum, all the colors we see. It's just the different wavelengths and frequencies of those lights. And so when the electrons drop those different energy levels, they're giving us different colored light. This first slide actually is an intro video that I did link into the original opening of this, or the original spot where you get your notes. So if you want to watch this video to get a more background, some more enrichment, definitely watch this video to understand that a little bit more. So our electron configurations that we've been doing show our electrons in the ground state. And the ground state is just when an electron is in its lowest energy level, the most stable state of the electron. So obviously, it makes sense that electrons are most often going to want to be in their ground state because it's the lowest energy level they can be. It doesn't take extra energy to be at a higher level. If they can just be at their ground state, following Aufbau's principle, we're going to fill the lower energy levels first, and they're going to start in that ground state. Electrons can move to an excited state where they move up an energy level though, violating Aufbau's principle, then they're higher energy level than their ground state, they're called the excited state. That's just when they're higher up than where they normally can be at their lowest energy level. That puts them in their excited state. It takes a lot more energy to get up there. They have a lot of energy when they're in their excited state. Just like anybody else, when you're excited, you have more energy. So then light is produced when the electron moves from that higher energy level to the lower energy level. It can go one level down, or it can drop a couple levels down, or it might drop all the way back down to its ground state. When it does that, it emits the energy in the form of photons. Photons are just light quanta, or particles of light. The different colors of light depend on its energy, which we'll go through later. Here's a diagram showing, this is one that will be on your test and on a daily quiz, so you might want to add this or kind of study this slide, put it on your cheat sheet. Electron configurations again show our electrons in the ground state. The ground state in this diagram would be the one closest to the bottom here, this darker green electron. That little dot there is your electron. Your ground state is the lower energy level. So here I have the orange. My ground state is pointing to this lower energy level. My principal energy level, N equals 1. The second one out would be my excited state, because that's where my electron is in the excited state. That would be N equals 2, because it's my second ring out. You can see when the lighter color here is showing where the electron was, it dropped back down to its ground state. It gives off this blue line here, blue squiggly line. That is your photon, or your particle of light. So when an electron drops from its excited state down to its ground state, it gives off energy in the form of light. So different lights, those photons, you can see they're wavy lines. So what's in the wavelength, it's usually the symbol of lambda. It kind of looks like a wave in a way, being held up by a little stick. Wavelength just talks about the distance from consecutive corresponding points on a wave. So like here's wavelength, the top point of the wave, top point of the wave. Your wavelength would be like measuring how the distance between those two peaks every time. And that's just you do the highest point because that's something that they can always reference and find each time they see the wavelength. Your amplitude, if you skip down, your amplitude is symbolized by A. It's the height of that wave. So there's a normal, so that would be halfway between. When you cut that wavelength, the waves in half, halfway between, and then up from that halfway between to the highest point, that's your amplitude, how high, the height of the wave. And then frequency is F. That's the measure of how many waves pass a given point per second. So if you're comparing this to like your heartbeat, your frequency would be how fast your heart beats. That would be your beats per minute. How often it goes up and down. Your wavelength would be the distance between, the time between your heartbeats, kind of. That distance between the two different, if you had a heartbeat monitor, the distance between the monitors. But your frequency would be your heartbeat, how many times it beats. So you can see here, like this blue one on top, this would have a shorter wavelength because it's closer. The peaks are closer to each other, way closer than the red one here. but then it would have a higher frequency because there's 3 different times that it's peaking in this amount of time that this picture is taken, versus the red one is only peaking about 1 and maybe half a time within that time. So higher frequency relates to a shorter wavelength. The shorter your wavelength, the more times you can get those waves in a certain amount of time. The longer your wavelength, like the red one, the fewer amount of times that the peak of your wave is going to pass in a given amount of time. We'll explain that, or we'll relate that a little bit later as well, but that is something you will want to know. The longer your wavelength, the less your frequency. The higher your frequency, the shorter your wavelength. Frequency is directly related to energy. Just like when your energy is high, your heart's going to beat faster. The frequency, it takes a little more energy to get those going faster and faster on that blue line versus the red line. Slow and long, quick and fast for frequency and energy. We have the different equations. Not going to do any calculations with these, but you will someday probably in your chemistry life. We have wavelength and frequency. The shorter the wavelength, the larger the frequency. Again, those are inversely related. One is shorter, the other one's longer, and vice versa. So you can see this sign here again. Remember, lambda, that's your wavelength. Wavelength is equal to the speed of light, which is what C stands for, divided by your frequency. And here's the constant for your speed of light. 3.0 times 10 to the 8th meters per second. That's how fast light can move. So if you do the speed of light divided by your frequency, that tells you how long your wavelength is. Any of you guys who remember math, you know that if you have one thing equals to another being divided, if it's on the bottom, you know that those are going to be inversely related. So when one goes up, the other one goes down. Energy and frequency, the higher the frequency, the higher the energy. So the more your heart beats, the more energy it takes to pump your heart and the blood into your heart. So we have energy equals Planck's constant, which is H. That's 6.626 times 10 to the negative 4 joules. You have Planck's constant times your frequency again. So you can see here, if you remember math-minded people, when they are not in different parts of the fraction or being divided, that they are going to be directly related. So energy and frequency are directly related. When one gets higher, the other gets higher. So how I like to look at this is on an actual spectrum and just look at it this way. So I'm looking at the waves down here. I would just sketch one of these really quick and keep it somewhere in your notes or put it on your cheat sheet and then label it. So you can see here I have really high frequency, high energy, short wavelengths. They're really close together. On the opposite side towards the right, I have long wavelengths, so bigger wavelength, lower frequency because less are happening per given time, and less energy because it's like long and slow. Here it's quick and fast, so high energy, high frequency, short little wavelengths. So that's like your kind of like short steps. Here we have long, slow steps, lower frequency, lower energy. The one cool thing you can look at when you're looking at the electromagnetic spectrum is you can see where all of these different frequencies and wavelengths fit onto the electromagnetic spectrum. The visible light, what we actually see, is only a small part of the whole entire spectrum. And we can see X-ray wavelengths and gamma rays are way over on this side. And then we have microwaves and radio clear on the longer wavelength side. So we have, if you look at your ultraviolet, is going to be right on the outside of our purple side of our visible spectrum. And your infrared is going to be right on the outside of your red part of our visible spectrum. And it goes from the highest frequency is going to be with purple, the lowest frequency and the longest wavelength is going to be your reds. And then everywhere in between is going to be your other colors there. So we can use those light waves to identify what element they are because they have a tendency, when light is emitted and passed through a prism, there's only a small number of discrete lines that we actually can observe. So the atomic models account for this phenomenon by proposing that an electron absorbs the energy and moves to an excited state. And when the electron moves to the lower energy level, the photon's emitted. Then we see these discrete lines, like in this atomic spectra here. The discrete lines are observed and not as a continuous spectrum, as in the top picture. This is because different energy levels in the atoms are quantized and they have specific values. So they're not giving off all of the colors in between. They have specific values, so you'll only see those specific lights. Finally, the energy that moves the electron to an excited state may be radiant, heat, or electrical, so different things can do that. So when you look at this continuous spectrum here, that's when we see the entire rainbow. That's produced when white light passes through a prism. White light contains all the wavelengths of visible light. So when you pass the white light through the prism, it diffracts the light and you can see all the colors. But when we look at atomic spectral lines, you only see the specific wavelengths of light that are produced based on what electrons they have and what their ground states are, and then how excited they get when we add that energy in the form of heat or any other type of energy form. So when you add the energy, those electrons go to, usually they have characteristic energy levels that they'll go to, and then they drop back down. They give off a very specific light color. Then those are unique to each element. So each spectral line is actually unique, and we can use it to identify which element it was or which compound it is. So here's an example here. By having electrons strike an atom, you can actually see the photons and see the emitted photons recorded by a spectrometer. We can do that in a simulation. But here you can see these are the different elements here. We have hydrogen, helium, lithium, oxygen, carbon, nitrogen, neon. You can see they're all a little bit different. They all have specific lines and colors that show up more than others. So when you see that, you can get an answer, compare it to that, to these lines, and then you can kind of try to figure out which element it is. So here's kind of an idea of how they do that. They fill some gas, add some light through the gas-filled tube, and then they can see what lights come up. Sometimes you can do it this way where you see which light colors come through, or you can see which light colors are not coming through. But the same idea for both.